Hello? All right, that's working. All right, so I'm talking about Wayland today, and I've talked about Wayland before at XDS, and I've talked about it at FOSDEM and other places, and I usually do an introduction of Wayland and try to talk about how the graphics stack on Linux has evolved over the years, and how we have kernel mode setting, we have derived drivers that we can use without X. But I'll skip past most of that today because everybody here are familiar with all these components and the history. So let's see. Wait, I lost a tab somewhere. All right, so this is the general Wayland talk. I'll skip past through this pretty fast. There's just a few issues, a few points I want to make, and then what I do want to do today is I want to try to actually take a closer look at Weston, which is our reference implementation of a Wayland compositor, and try to see what features we have in there. And oh, here. Okay. That was unfortunate. But so So again, the idea is that we have an architecture today where a lot of the components are split out, and we can actually build different display servers quite easily now by opening up the DRI device, starting to use kernel mode setting. We can run EGL on kernel mode setting. We can share buffers between processes. We have EVDEV devices in the kernel, so we have all the building blocks for a display server. And the toolkits today are very big and very self-contained in a way. They do a lot of their work internally. They don't rely on sub-windows or client server-side rendering. So toolkits are pretty easy to bring over to a minimal subsystem. So Wayland is really just the glue code that sits between these components and makes it possible to more or less have the desktop and the infrastructure we have today, but just without X. So in a sense, it's more about removing X from the stack we have today, and it's not about adding new display servers. It's more about putting the pieces together without X. So of course, the big thing is that we make the compositor the display server. In X, we have an external process that's a compositor, and compositor talks to X to get input events, to get an output service to render to. It talks to X to get textures and from all the different clients that it wants to render. And the clients talk to X to push their rendered output. They talk to X to get input. So X is the middleman that sits in between apps and compositor to send input events and textures back and forth. And X is also a middleman between the compositor that wants to render and control video overlays and the hardware, the kernel mode setting, where we actually do these things. So the compositor goes through X to do its output, to render and present the screens that it renders, and X then talks to kernel mode setting. And same thing for input. The compositor really knows where input should go, but it has to. The input still goes through X. So in many ways, X just sits there in the middle and kind of gets in the way for what we want to do. So, but all this is stuff that most of us we know how these things work, and we know how we can piece it together. And So the only thing I really want to say about general Wayland is that we're on track to release 1.0 soon. And 1.0 of Wayland means that we're going to make the protocol stable. So right now we are in a development mode where we basically can break the protocol if we want to. We can remove a request. We can add an event. We can change interfaces and requests. And this is hard to keep up with for toolkits that want to run on Wayland. So what we're going to do now is that we're going to move to a 1.0 release, which more than anything just signifies that we start developing the protocol in a backwards compatible fashion. So the protocol is in many ways inspired by the X protocol. We have we call them interfaces, but these are in many ways like an X extension where you can look up if an interface like that exists, and you can see the version. So we have the option to introspect and add new interfaces later on. We can version these interfaces, add requests or add events. So we have a lot of versioning built in. We have a lot of options to extend the protocol after 1.0. So what we're really just saying with 1.0 is that we're going to stop breaking things, and the toolkit, the porting efforts that have brought the different toolkits to run on Wayland will not. We don't have to redo that every time we change something. So that's the short-term plan. It's going to come out in a few weeks, and it's going to be very close to what's currently in Git master of Wayland+Weston. So from there on, it's going to be a lot more easy to track Wayland. So that's basically all I want to do for the general overview. And what I want to talk about next is well, I had two things I wanted to present. One thing is the video stuff that we've done recently, and so the way buffer sharing works in Wayland, and this is I don't know how much you all know about Wayland, but it works a lot like what Keith and Eric was presenting yesterday about DRI3, that buffer management is entirely in the client. So when a client wants to render something to a Wayland surface, that client has to go out and allocate the buffer he wants to render to. So if you want to push a color surface to Wayland, you have to allocate that color surface, render into it somehow, and then once you render that entire buffer, once the content is complete, you pass that buffer to the Wayland server, and the Wayland server will then present that on screen, so that we go from whatever was ever in that surface before to the new buffer. So we replace the entire buffer contents every time the client pushes something. And that's the basic idea. Allocate buffers in the client, render, and then push the final result to the compositor once the frame is complete. And that's essentially the only mechanism for presenting contents in Wayland. We also have a notification mechanism that applications can use to say, I've pushed this new content to you. Can you notify me when it becomes visible? So since Wayland is all frame-driven, then that typically happens when the compositor renders a new screen and page flips to that screen. So at that point, we send that event back to the client to say, your surface is now visible. And then the client can go and render the next frame and throttle animations and updates to the frame rate. So what that is essentially a pretty good presentation API. We get a timestamp with that event, so we know when that buffer became visible, and we can push a new one. And if we want to render every second frame, we can just skip a frame. So we have a lot of control client side over the buffers, whether we triple or double buffer and how often we render. And we get a timestamp back that tells us when the content became visible. So this is actually something that's pretty critical for doing animations, and it's also a big part of a video presentation API. So the difference in Wayland is that instead of having this part of a specific rendering API or a video decoding API, this is the core mechanism in Wayland. This is how everything is presented. So when we want to add video support to Wayland, we don't have to come up with a new presentation mechanism. We essentially just have to support different color formats for the buffers you can push into the compositor. So initially, Wayland only supported RGB buffers or ARGB buffers, but with the video support, we added support for pushing YUV buffers into the compositor. So how video works on the Wayland is then that the decode library will go out and allocate a buffer that has the right stride and pitch and layout and so on, then decode a video frame into that buffer, and then pass that buffer into Wayland. And then it gets a little tricky because video buffers are often laid out in different ways. You can have packed pixels like we have from RGB, where you have a tuple of 4 bytes that gives you the RGB value, but it can also be planar, where you have different planes for the different color components. So you can have one plane that has a little buffer here that has the Y component, and you have 2 smaller buffers that has the U and V components. So we end up having to support different ways of laying out the samples. So it's possible that you have one of the planar formats, or you have a packed format. But either way, the application can, or rather the decoding library can choose the format that it can work with and decode into that and pass that buffer to Wayland. And again, the buffer passing is the same as we do for everything else. It works by sharing handle to the buffer, and we use gem handle for that now. So it's still a gem buffer object. It's just maybe has several planes in it, and the colors are YUV instead of RGB. So that's basically all there is to say about the core mechanism for video. Then on top of that, we have for Intel we use libVA as our decoder. So Granoli, who works on libVA for Intel, he's been writing the backend for libVA to actually do this allocation and decode into the buffer. And then on the compositor side is where it gets interesting, because once we get that buffer into the compositor, we can't just texture from it like we normally do, because now the buffer is YUV, and the buffer may also be planar, so we have to set up the texture units differently. But we have Mesa work that we've done that allows us to basically query what the buffer is like, and we'll get information back that tells us this is a YUV buffer, and you need to use 2 samplers to sample from 2 different planes, or 1 sampler. So we have the Mesa. It's a Wayland extension that lets us get this information out of the buffer and then set up the shaders correctly. And then we can do the color conversion in the shader, going from YUV to RGB is a pretty simple combination calculation that we can do in the shader. And then what we have at the end of the day is basically decode into a buffer on the client side and texture out of that on the compositor side. So it's a very efficient code path. The video data never hits the CPU in any way. It gets decoded into a gem buffer, and then we texture out of that buffer directly. So it's a pretty efficient path. And of course, we then use the standard Wayland presentation mechanisms to push that buffer to the compositor. Every time we decode a new video surface, we pass it to the compositor. Compositor eventually tells us when that surface was displayed, and we can feed that timestamp into whatever throttling and timing mechanism the media framework has. So in this case, GStreamer. GStreamer has libVA integration, and this whole thing is hooked up so that we feed back the timing information into the GStreamer software, PLLs, and the whole thing works pretty well. Now the interesting thing is that on the desktop, we've gone from having different types of overlay to using compositors and textures video for most things. And it's a very flexible and nice way to work with video, because you get it through the GPU, and you can rotate it, and you can wobble the video, make it transparent. So you got a lot of options for transforming and playing with that video, but it's also not a very power efficient way. So even for laptops where you have a lot of battery power and a big GPU, you may still want to use overlays, because if you want to watch an entire 2-hour movie, you may want to make sure you have enough battery to last through that movie. So it makes sense for laptops, but of course even more so for mobile devices, cell phones, tablets, and embedded devices, car, media players. All these places, it makes sense to try to go for a lower power mechanism. And this is still something where hardware video overlays are way better than textures, because if we don't have to pull the texture, let this big video frame in through the GPU, do the color conversion, and write it back out, if we can just ask the hardware to scan out from that YUV buffer directly, then we have an even more efficient path, and we don't go through GPU. And in some cases, we even get better quality because the hardware overlays have better filters, they have better scaling performance, better scaling quality, and of course they use less power. So it makes sense to use these overlays wherever possible. And it's actually something that Wayland is set up to do pretty well. Because in Wayland, the compositor runs on top of kernel mode setting. So what we can do here is we can ask kernel mode setting if there are any kind of overlays available. And one of the recent things that Jesse Barnes added to kernel mode setting is support for this thing that we call DRM planes. So a DRM plane is basically a rectangle on a screen where you say that the pixels in this rectangle come from a different buffer object. Normally, when we page flip or set a mode, we have to specify a buffer, a gem buffer that provides the pixels for that output. And normally, all the pixels for that output comes from the same buffer. So in case of this, all these pixels are in one big buffer in memory, of course. But with planes, we can actually say that this rectangle here on screen, over here maybe, or whatever, takes pixels from a different buffer object. And once we do that, we can also say there's a different color format, or maybe we can scale them. So there are some basic properties that most overlays have. Of course, the overlays are one of those features where every chipset has different functionality. So what we have in KMS is just the basic common subset that most overlay hardware supports. So we can put these overlays in different places on the screen, but we can't really capture all the esoteric and features that a lot of overlay hardware has. So in many ways, kernel mode setting provides us a lowest common denominator overlay, but it's still something that's worthwhile hooking into. So what we do is that since the compositor sits on top of kernel mode setting, and we have the scene graph, the stack of surfaces in one hand, and we have kernel mode setting in the other hand, we can look through the scene graph and to see, are there any surfaces here that has a color space and then are not obscured that would be suitable for an overlay. So we have the option to actually per frame look through the surface stack and see if any of the surfaces would be beneficial to put in an overlay. And we do that, and if we see a YUV surface, for example, coming in from a video player, and we have an overlay that can display that YUV surface, we'll match that up so that the frame coming from the video decoder will go directly into a hardware overlay. And that's when we hit that low performance or low power path that I just talked about. We get all the benefits from using an overlay. And again, it's not something that the application really has to care about or worry about. With X, you say, I want to use an XV adapter or something. You have to explicitly select an overlay. You have to work. Well, I guess we could be made to work with X with a few tricks, but the idea here is in Wayland is that you don't do anything special. You just give. Wait. Hello? Yeah, you just give the compositor a buffer in a different color format, and then the compositor will, if possible, use that. And the thing is, it doesn't even have to be a different color format. If you have an opaque surface, for example, that could go in an overlay, then we'll use that, and that's something I can demonstrate that now. So here's a spinning triangle, and this surface is is an RGB surface, opaque RGB surface. And on this Intel hardware, we actually have overlays that can take either YUV surfaces or RGB surfaces. So in this case, when my terminal here is on top of the other surface here, well, there's nothing we can do because we can't use a hardware overlay. But when I pop this one on top, we flip that surface to use a hardware overlay. So now this is actually not getting composited anymore. We're just changing the overlay every time a new frame comes in from the application. We just flip the overlay to that next frame. And now this is compositor is not doing any rendering now to make this happen. This is just spinning, and the compositor is just page flipping, doing a 1 octal per frame here. And I flip it back here, and it just seamlessly goes back into rendering this spinning triangle as part of the rest of the frame buffer. I don't know if some of you noticed, but when I do go to an overlay, the frame rate actually drops here. And the problem there is that we don't have page flip for sprite for DRM planes yet. So when we do this, we actually go through the full mode set path for this sprite, and it ends up taking 1 or 2 frames extra, which means that we don't actually flip this every frame. We drop to 30 frames per second here. And that's something that Rob will talk about tomorrow with his nuclear page flip, because we have a page flip ioctal in the works that will let us page flip everything on screen in 1 ioctal. So instead of trying to update different planes with different ioctals and use mode setting, we can actually submit an ioctal to KMS that says change everything on screen. So we can say move the cursor down here, or change the cursor image from a hand to an arrow, or we can say page flip this sprite, or move the sprite over here, and we can page flip the main frame buffer. So everything that we see on the screen that's controlled by kernel mode setting, we can change with 1 ioctal, and we know that they're going to change together, and we're going to get an event back. But that'll take care of this performance issue here. But I won't go into that too much. That's Rob's talk tomorrow. So I can just show the video support here, and I just need to make a small change here. And so what this is GStreamer using libva to decode, and then pushing the YUV frames to the compositor every time there's a new frame ready. And this is not using an overlay, and we have a slight incompatibility problem in our hardware, where our hardware decoder can't actually decode into a format that we can use with our overlays. So what's happening here is that the hardware decoder gives us a YUV buffer, and we then do texture video to get it on the screen. So it's not the most optimal path here, but it's still very efficient code path. So it's full 1080p video, and it's actually, it used to be less. It used to be just 3% for Weston and GS3 launched. And of course, the compositor also uses more CPU when it has to put this panel and terminal on top. But we have a pretty good video playback pipeline here. And of course, there's no tearing or anything because it's all paste flipping, so everything gets rendered to a back buffer, and we paste flip to that back buffer. So we never see any tearing or artifacts here. All right, so what I wanted to do for the rest of the talk is just go through some of the features we've done for Weston. And Weston is as I said, is a reference compositor for Wayland. It's kind of the vehicle we've been using for testing the protocol. And whenever we add a new thing to the protocol, we implement it in Weston. And we have a toy toolkit where we can write small clients, like this terminal here. So whenever we want to verify the protocol, we use Weston first to implement the features. And initially, Weston was a throwaway thing. Intention was to have something that we could test the protocol, and then eventually we could have Kwin, Metacity. These existing X compositor could become X compositor, could become Wayland compositor by changing how they, instead of talking to X, they talk to kernel mode setting, talk to EVDEV, then use the Wayland protocol to pull in clients like Weston does. And that's still an option. That's still one way to go. And I certainly expect that if GNOME and KDE are to become Wayland capable, that's the path they will take. But what also became obvious during the development of Weston is that Weston is at a point where it's functional and featureful enough that it's perfectly useful for a lot of things where you don't need a full desktop. In fact, if you do need a full desktop and are happy with something like XFCE or smaller environments, then it would probably be possible to pull in the XFCE panel and XFCE file manager and work on the Weston. But Weston is also a very good fit for embedded use cases. If you're building a set-top box and you want a multi-process display model, then Weston is a good fit for that. If you're building a car and you want to throw a browser up here and then a video player and then go back to your main UI, Weston is a good fit for those cases too. And it would be a good fit for tablet and phones, except if that market seems to be kind of occupied. But anyway, so Weston is in many ways a very flexible component that can fill a lot of, can sit in a product where you need some kind of multi-process display, but for some reason don't or can't use X or don't want to. So with that said, let me just show a few of the things Weston can do. Features.txt. This is my presentation. So one of the things we did, or let me say Pekka Parlanen from Collabora, he jumped in and started working on Weston. And one of the things we have in Wayland is that we don't give global coordinates to applications. We don't tell applications where their window is on the screen. So as an application, you don't know where you are. You don't know if you're sitting up in the corner, if you're in the middle of the screen, and you don't know when you get an input event, you don't know the global coordinate of that event. And part of this is that if you did that, applications will start assuming that you can go from global coordinates to local coordinates by just subtracting your window position from the global coordinate. And applications will make those assumptions. And under X, that's basically the reason we could never make X work with input redirection. Because even though we could potentially put up a grid of triangles that would tell the X server how a certain window was transformed, and X could use that grid of triangles to go from global to window local, we wouldn't get rid of all applications thinking that they know where they are on screen. So this is one of the things in X that basically, it's not a technical problem. It's a problem that all X applications out there assume they can make these jumps back and forth between global and window local coordinates. So one thing we do in Wayland is that we just don't give ever we don't ever give the applications global coordinates. So this means that we can actually have working input redirection. The other part of working input redirection is that since the compositor is responsible for pulling events from EVDEV devices and figuring out which window to send them to, the compositor also knows exactly how a given window is transformed. So if it's scaled down, rotated, or wobbly, or whatever, the compositor knows what it's done to that window, and it knows how to move back and find the window local coordinate for a global coordinate. And that's one of the things we got stuck on with X2, because X only understands rectangular axis-aligned windows. There is no such thing as a rotator window or a wobbling window in X. But yet X is where we decide where to deliver coordinates and how to transform them to get window local coordinates. So there's a disconnect there. And with Wayland, we can solve this the right way, because the compositor pulls in the input event and can figure out how to turn that from a global coordinate into a local coordinate. So one of the things we have is rotation here, and it's in many ways it's probably it's not a useful feature as such, but it is pretty cool that you can rotate a window then like that and then still have input redirection working. And also, since we have, I'm jumping ahead here to a different feature, but we do have the options of pulling in X clients. And since X clients have the same, they go through the same, they get events through Wayland, we can actually rotate X term and still have input redirection for X windows working. Of course, we won't get around the fact that at some point X term might assume that you can go from local to global coordinates or the other way by just adding its position. But for many cases like input events where they don't actually need global coordinates, we can certainly have this stuff working pretty well. Oh yeah. Let me do that. Yeah, let me do that over here. It looks better with this guy here. So, let me see. There. So, okay, let me just good option here to just talk about another thing that's highly debated when it comes to Wayland and how things work. So in Wayland, applications render their own decorations. So this terminal here doesn't just give me the black window inside the application. It gives me the entire frame around it as well. And one of the reasons for that is that if we do that, we get the entire window is one big texture that we can sample from. So if we want to rotate this window like this, then this edge here along the black content of the terminal and the white title bar, this edge is actually inside a texture. And when we render that edge, we use bilinear sampling from the texture to get the color value there. So that means that we end up with a nice smooth edge instead of a non-anti-aliased edge. The other option would be we could render just the black content of the window as one big GL primitive, and we can render the title bar as a different primitive. But then the problem with that is that the GL primitive edge is not anti-aliased, so we get that nice awful jagged edge. So by having decorations inside the buffer, we have the option to actually have a really nice looking rotated window. Again, where the rotated windows are relevant is a different discussion. But and of course, once we go back to non-transformed, this edge is actually falls on a pixel boundary anyway, so there is no benefit if you're not actually rotating the window. But that's one of the ideas there. Okay, so another thing we added recently is, and this is something X has had for a long time, X render. We can rotate windows. Oh. So again, nothing new here, but since this is done by the compositor, it is fairly efficient, because when we go from a client window to the compositing the full screen, we have to texture anyway. So we have the application content, we have to put it on screen, and when we do that, when we render that, we just set up a different GL transform, and we just render the whole thing as we normally do. So there's no extra copy here. There's no extra step to rotate things. We just configure the GL matrix to rotate accordingly. And of course, some desktop elements like the background, the panel, has to know how big the desktop is and allocate the buffers accordingly. So, a question? Yeah, that's a good question. So, subpixel rendering is communicated to the clients as it is in X. We communicate per output what the subpixel layout is, and we communicate how that output is rendered. So from that information, the client is able to determine how to do subpixel rendering correctly. Oh, if you rotate, well, so the output rotation here is always in multiples of 90 degrees or flipping. Excuse me? Oh yeah. So if you rotate like this one, yeah, this is hard to. There we go. See, now it's almost back to normal. There. So yeah, in this case, suppose we actually rotated this 90 degrees and it snapped back to pixel aligned. There's nothing you can do about that in that case. But also, you can render pixel aligned if you're wobbling or if you're wrapped around a sphere. So there are limits to how we can do that. But so pixel aligned again is optimized for the case where you're actually non-transformed one-to-one with the pixels on screen, and you get the subpixel layout. You get that from Wayland, and you get information on. You don't get global coordinates, but we will tell you which output you're currently on. So if you're on this output here with one subpixel layout, and you suddenly move back to my laptop screen here with a different pixel layout, you do get an event to tell the application you're on a different screen now. And then you can re-render with the subpixel layout for that screen as you move around. Question here?
Why is this crowd? Why is this per output? So you rotate your complete screen, and then you just rotate a window 90 degree into it, and you get a different subpixel layout which actually fits, matches the screen somehow.
So
what push this down to the window level? So if they're aligned to 90 degrees and rotating.
You're saying why is the subpixel layout per output? Yeah, that's a good. I mean, it is inherently a property of the display. Well, of course, once you start transforming windows, it's hard. We didn't really. I mean, there's so many other transforms you could do where it just doesn't apply at all. And then
there's some special cases where you still could do nice rendering. Well.
Yeah.
Where you just
it's true, and
transforms in maybe steps of 90 degrees or something.
And maybe we can add that. It seems like right now it is. With that, I think there's a lot of details you could chase where you could get correct, better rendering in some cases. But for now, I think we reached a good enough point, and I think there's room for optimization. We can do better, but I think it's not the most important thing right now.
Okay. Thank you.
You're right. Over there.
Is it possible to have different transform for different outputs? So, for example, like having your laptop display and the projector running at different resolutions, and still having clone mode the picture?
Oh, we don't have clone mode at all.
Okay.
But yeah, you can set different rotations.
That's useful.
Yeah. I mean, clone mode is useful for cases like this, where I'm presenting here and I want my laptop here. But other than that, like for anything where you're sitting at your desk or something, it's not really. I mean, it's not really useful. It was something. It started out as a restriction of how we could do mode setting, how we could couldn't reprogram the mode, but we could add another output to the current mode, the current setup, and it was just. I think it started out mostly as a limitation of that, and also because we couldn't have side by side because we were hit a stride limit in early hardware where you couldn't render more than 2K pixels, for example. So we had to do clone mode in those cases. But today, also Western doesn't use one big frame buffer for multiple outputs. We have one frame buffer per output. So when I'm moving around over here, rendering here, we only page flip that CRTC, only that buffer. So we don't have that stride limit anymore. But as for clone mode, we just don't have that. It's not like we're morally opposed to clone mode, but it just doesn't seem very useful right now. Or
you get the same picture on the projector and on your laptop?
Yeah. So in this case, it's useful where I'm presenting and I want to see what's on the projector on my laptop, and I want.
And they don't need to have the same resolution. Your picture on your laptop might be a bit stretched or something like that, but it really is useful.
No, it's useful for presentations. We don't have the feature right now. But again, it's something that we have a lot of flexibility in how we implement, if or when we implement it, because we don't have to use the same frame buffer. We can render the buffer again at a different. We can have it look into the same scene graph from two different renderings. We can render it rotated up here on the display. We can render it normally on the laptop. So we have options. We don't really have that feature right now. Oh, the desktop? You mean the no? So but that's just because that's part of the desktop. We don't rotate that. And the idea is that this is not a way to put your panel on the side of the window. This is for cases where your monitor is rotated. So you have to imagine this as you have a panel that's mounted like this in a car or in a tablet or something, where you end up with a panel that's physically rotated. So when you look at this, you're actually looking at it like this. It's not a quick hack for putting a panel on the side of the monitor.
What will happen with the multi-head or Jinarama? If we can in multi-head or Jinarama, if we can rotate and fit two windows in a different angle, then it can be good for market for some products to sell.
Do you want to render the background at a different angle for different outputs?
Let's say we have the two multi-heads.
Yeah.
Two display or two multi-heads, or we have Jinarama, or maybe four display fitting into one Jinarama window, and then we can do some animation or rotation on that kind of things. Then this idea could be a selling point in market.
So to animate the background transition,
or maybe the window itself, the front window itself, if we can rotate.
Yeah.
Is it possible?
What do you mean?
Let's say we have the two display, two.
Yeah. I don't know. I mean, this is what we have now. You can rotate per output, so you can configure different outputs how they're rotated or flipped, and they still get stitched together in one big workspace or geometry, and that's the feature we have now. On top of that, you can do a lot of things. But we, yeah, I guess I'm not completely sure what you're asking. But.
So let's say we have that four multi heads,
yeah.
four display, and we want to change the direction or rotation, and come up with the unique kind of display with kind of some animation we want to give.
Yeah.
So could we do that? That's the question.
Yeah, yeah. Again, the background here is provided by a regular application. And if you rotate the display on the fly, we will send out notification that the display is now rotated. And that the application that provides the background is in a good position to animate the background to match the new rotation as it gets rotated.
Okay.
So that's possible. You could hook up, if you think about rotating a display and then animating the change there, that's definitely possible. And we do send out events to update applications when things get rotated. So I think we have the infrastructure to do that. Okay, so I'm going to move on with X integration. And this is something that I'm going to... Actually, let me just switch this back because I can't use this. Okay, so and this is something I'll talk about a bit more about in later today. But we have X integration here, and it's a lot like what we saw earlier today with the XCWM library. But what we have here is we use the X server and we use a X Wayland module in the X server that lets us pull in X windows as Wayland surfaces. So there's essentially two ways to go about this. One way is you pull in the entire X server with the root window, and you show that on the Wayland display as a full screen window. I'm not sure if that works right now, but I can give it a... Right. Yeah. No, it doesn't. So we used to have that feature, but it's not. We don't use it regularly, so it's not working right now. But this is part of how you pull a full X server in as a client of Wayland. What we do use is the rootless X server, where we use. It's basically the same code base, but it's just set up so that the first thing the X server does is redirect all its top-level windows, and that means that, as Keith explained earlier today, that when you do that, each window gets a different pix map that backs the window content instead of all the windows carving pixels out of the front buffer. Then now every window has its own backing pix map. And the Wayland integration code in the X server then takes that pix map, which is a gem buffer, like anything else we push into Wayland. We take that pix map and push the handle to Wayland. And from Wayland's point of view, that X window now is just another Wayland surface that it can. The window content is available as a GL texture without any extra copying, without any performance loss. Whenever the X server renders something, the X server will inform the compositor, Wayland compositor, that I just damaged this surface, and or maybe if you paste flip a buffer, that you'll say here's a new backing buffer for this surface. But from the Wayland's compositor point of view, it's really just another Wayland surface. So, and as for input events, we get input events from EVDEV devices and turn them into Wayland input events internally. And what we do, we send out these events to the X surface as any other Wayland surface. And inside the X Wayland integration code in the X server, we'll turn these input events from Wayland into X events. So from X point of view, you're really just getting input from a different input device. You're not talking to EVDEV anymore. In X, you get input events from a different EVDEV device, and you don't push your buffers to kernel mode setting anymore. You push them to Wayland. So it's a very efficient implementation. There are essentially no performance overhead when compared to running on X with a compositor, because instead of having the application talk to X and then the X talk to the compositor, we now have applications that talk to X and then X talk to the compositor. It's just the compositor is no longer an X line. So it's essentially the same code path, it's the same performance, and we're using the same 2D drivers as well. So there's a small change to the Intel DDX driver, for example, that lets you run the existing acceleration code in the DDX driver, whether you want to use Glamour or UXA or SNA, which other acceleration backends we have. All those just work because they render into a gem buffer, and we push that buffer to the compositor. So however we render into that compositor, it just works with Wayland. So there's a display set here, and then as you saw before, I can run Xterm. Xterm comes up. I can run GLX gears. GLX gears run, and of course the gears are hardware accelerated, so it's the same way as we can use the 2D driver in X. We use the 3D driver in X that renders into the pix map that X manages, and we then pass that pix map to Wayland, and Wayland textures from it. So it's very similar to how we have direct rendering, accelerated direct rendering under a compositor in X. Question? Sure. The GLX geared window is just another Wayland client, right? So if I want to rotate it, I can rotate it. Put it down here. And I can rotate the gears within the window. Oh, that's true. Maybe I can rotate the gears and rotate the window. There we go. But we can run regular gedit applications, X apps, and we can. Yeah, XIS is interesting because XIS doesn't really work except when I'm over a window that's also an X window. So XIS relies on being able to just grab the coordinate of the pointer at any time. But if we're not moving the pointer in an X window surface, then from the X server point of view, the pointer isn't moving. It's just stuck somewhere. So if I move around now, the XIS, they kind of just sit there. If I move into Xterm, you can see how they move around. And what's interesting is that Xterm is actually sitting at 0,0. It's sitting at the origin of the X server. So when I'm mousing around up here, I'm actually at 0,0, even though the Wayland window is down here. And when I go over here, XIS is also sitting at 0,0. So
what about supporting the shape extension?
Oh yeah, I don't think we do that. O'clock. So this is actually a good segue into the next topic, which is that to do this, we have an X window manager inside Weston. So we could probably share some work there with XCWM that we saw earlier today. But we do have an X window manager inside Weston that talks to the X server, redirects the windows into a parent window, draws the decorations as using X primitives. So there is a X window manager that talks to X and manages the windows at X the way X clients expect, and it draws the shadows and the decorations and all this stuff. And it reads out X properties, it sets X properties, and it remaps and does all this low-level dirty work that a window manager has to do. And one of the things we're talking about right now is that we should probably move this work out of Weston, because right now we have it's a very bad setup, because we have We have Weston running as the display server. Then we have the X server as a client of Weston. And then because Weston is also the window manager, Weston is also a client of the X server. So we have this kind of deadlock waiting to happen. As soon as we block to read a property from the X server, and the X server blocks on doing something from Wayland, we're going to end up blocking. So we're going to rearrange how that works and push the window manager out in a separate process. But other than that, it's going to work pretty much the same way. Another thing that we probably want to do there is, as I said with XIs, all applications, they just sit up at the origin of the X server. They're not moved anywhere. So if I move X term down here, X term under the X server still thinks it's sitting at the origin because there's no way to push those global coordinates to the X server as a client. But that actually breaks some things when you pop up menus. Then, okay, that didn't work. But the X clients today look at the geometry of the screen, and they look at how panels are laid out, whatever else is on the screen. And when they want to pop up a window, they try to see, is this pop-up going to get clipped by a screen edge or a panel or something? And then they move the pop-up to the other side, or they move the pop-up up above the window. So those small details are pretty important for actually having usable menus, and we need to make that work too under X, under Wayland. So we need to push the position back into X so that X clients can do this kind of calculations. But we don't want to do this for regular Wayland clients. The problem here is that X clients are built in a way where they don't have any higher level mechanism for placing pop-ups. So we need to make this work so that X clients will work. But for Wayland clients that are aware of this, we have a positioning mechanism that lets the client ask the server if this pop-up is going to be visible or if it's going to be obscured, and then they can place it somewhere else and try again. So there is a handshake mechanism for positioning pop-ups according to global screen geometry without actually having to know global coordinates or know what else is on the screen. I don't have any X games installed here, but it would be kind of cool to show one of a GLX game running at the same frame rate as it runs as under X. But I don't have anything to show that off. But let me just say again that there is essentially no. It performs the same way as the applications do under X under a compositor. So it's a very efficient architecture there. Okay, so I guess I already talked about these features here that since the compositor sits on top of kernel mode setting, we have a lot of control over how we present and how we use kernel mode setting, and we can hook into stuff like sprites because we have all the kernel mode settings at our disposal, kernel mode setting features at our disposal, and we also have the stack of surface that we need to render in the other hand. So we can really match the surface stack against the kernel mode setting features efficiently and try to avoid rendering as much as possible. Input is done by reading EVDF devices. We read out events from the input devices, and we move the mouse cursor around, and it's pretty standard how that works at least for pointer and keyboard. Keyboard goes through libxkb common, which is something that we worked on with Daniel Stone, and it's basically the core functionality of XKB pulled out into a library. So we can point this library at a keyboard map, have XKB common pass up the keyboard map, and then we get a little state machine back where we can feed in key codes, and then XKB common will track the XKB state and spit out key sums in the other end. So when you get a hardware scan code, you feed it into XKB common and we get the key sum back out that we can use in applications. And this is something that that we're using in the compositor for key bindings and keyboard input, and it's also used in the clients because we send out the hardware key codes, and the clients will then have to pass the key map and do the translation themselves. We have support for touchscreens and touch devices where you have a direct touch interface where you're touching the screen, and we send out those coordinates as multi-touch. And it's fairly standard. It looks a lot like if you see what iOS and Android have. It's very similar to those event protocols there. Hotplug works, and the same thing for KMS. Hotplug of screens, hotplug of input devices work because we hook into UDEV, which gives us all the hotplug events we need, and then we go out and discover what got plugged and hook it into the Western infrastructure. Oh yeah, so we have another cool feature here that we can zoom the output like this, which is like a typical compositor feature where you want to zoom in and this actually has a cool feature that it follows the what you're typing here. Oops. Well, it's a little confusing, but if you're typing, it's pretty cool that hello world, that you can see what's going on and you can still mouse around here and then you type something and it jumps back. So that's it's pretty cool. You can it's useful for debugging when you want to zoom in and see what is actually rendered. Another thing we have is we have a built-in screen recorder. So if you want to capture what you're doing into a video, that's built in, and again it's pretty efficient because it's built into the compositor, and we render a frame, and we're pretty efficient about only rendering things that changes, and then when we then have a screen recorder built in, we want to capture. We only capture what changes as well. So we read the pixels out of the buffer we render into, but we only read the pixels that we know changes, and we keep track of all the previous frames, so we can always construct a full video stream out of those delta information. But it's a very compact and efficient way to do screen capture. And for unless you're doing a full screen video play, well, even for full screen video, it works surprisingly well. So you can really capture what's happening on screen, and it's a lossless format. We save it to disk, and then we have a tool that will take that capture and spit it back out as a YUV stream. You can feed into different video encoders. So I think I can try to do a capture now. Just so there's a hotkey to start the capture. And it captures all the spelling errors too, unfortunately. But there, and that gets dumped to a file called capture.vcap. And we can decode it. See, it's 60 frames total, and if we dump it to YUV for MPEG-2 is the name of the format, we can feed that into an encoder to get a WebM file or a OGG file. We can also feed it into this little client here. That just play back the. Oh, I think this is a different capture, isn't it? Okay. Oh, the compositor picks the file name. I think it landed up here. There we go. So this is totally confusing, but it is a window playing back here. And there are all my typos coming there. Hello, XDC. So, so that's a very useful feature that to have built in, that you can capture everything, and it works at a pretty high pretty high performance capture tool. And it lets you pull out single frames as ping. If you see a glitch somewhere, that rendering glitch, you can capture that, and you can get the ping file out and have a closer look at what went wrong. Another thing about client-side decoration that comes up is that what if we have a client that goes inactive? So right now, when I click here, the click in the title bar, that click goes to the client, and the client tells the compositor, please move my window. And the compositor is then responsible for actually figuring out where the window can go. So the compositor could do snap to this window edge here, snap to this window edge, but it just doesn't right now. But it works by the client asking the compositor to move, and by the compositor actually, the compositor is in charge of figuring out where the window might go. So it has all the features of window manager moving. But the weak link, of course, is that the client has to intercept the click here to move the window. So if the client is locked up, it won't be able to do that. It won't be able to tell the compositor to move it. So what we have now is there's many ways to get around this. If I stop it now, we can see I mouse into the window here, and I get this little busy cursor here because the compositor pings the window. And once we enter a window, if we type into a window, if we get keyboard focus in different key transitions in that window's lifetime, we ping the window and to see, are you still alive? And if the window's asleep, we won't get a reply. And if we don't get a reply within a few hundred milliseconds, we just decide that this window is no longer inactive. But there's nothing to keep us from raising the window still, or just moving it when we click somewhere, so we can still interact with the window, move it out of the way. So, or we could also have like a special menu that pops up if you try to interact with an inactive window. We can handle that like that. But right now we just put up the spinning cursor and let you move the window out of the way. You can resize the window, but that's because whenever you resize the window, you need the application to actually give you the frame at the new size. So there's no point in trying to resize it. And of course, when we say foreground, it goes back to normal, and now we're back to just spinning the gears when we try to click in here. So, and this is just one approach to solving this. You could put some regions up here that says if I click the close button and nothing happens, if I get a click in this window, in this region of the window, and the window is still around 1 second later, it's dead, and we have to kill it some way. So, for example, if I suspend it again and try closing it, it doesn't actually go away. So there could be something that handles a click up there and kills the window, or pops up a force quit dialog. And what we have now is just a secret hotkey to just kill the window, because everything here is a unique socket, so we can get peer credential. We can see what the process ID is on the other side. We just kill that process ID if we. So, I mean, that's how force quit works. If you're running Metacity or any other window manager and you're trying to kill a window and it doesn't respond to the delete window X client message, you end up just killing the PID that the client put in that window. So the client in X, there's no reliable way of getting the PID of a client, except the client can set a property on the window that makes the PID available to anybody who reads that property. And then that's what Windows managers use to force kill clients that don't respond. So it's pretty much the same thing there. Then we have, I showed you video support, and we have input methods, something that we're working on with the guys from OpenIsmus. So Jan is here today. He's been doing most of the work here, but we do have the beginnings of input methods and the on-screen keyboards and those things, where we have and so far all the examples here are just simple examples, toy examples. But of course, like anything else here with Wayland, the idea is that this integrates with a toolkit eventually, so that you can integrate with a Qt on-screen keyboard, or the Qt input method, or GTK on-screen keyboard, EFL on-screen keyboard. So these existing components can hook into this. It's a different protocol, but it gives you the same mechanism. So this just starts up the on-screen keyboard in the background, and the on-screen keyboard is a special client that the compositor knows about. The compositor knows that this client provides some services to the compositor. That is, the compositor in turn advertise on-screen keyboard to all the other clients. So we can run an editor here that relies on the on-screen keyboard. So I want to edit this entry up here, and there's the on-screen keyboard. And I go back here, and it goes away. But I want to edit this one now. Yeah.
Don't worry, it's recorded. You have all the time.
Yeah. No, I think I can reproduce this one, but yeah. I think I saw it before, but let's not do that again. Yeah, I'm holding it wrong. Yeah. But anyway, let's just try one more time here without. So yeah, we click here, and of course we can edit stuff. Well, again, the keyboard here and this editor is just a couple of small applications that we wrote just to exercise the protocol. This is not a real on-screen keyboard. This is not a real input application. This is what we use to test the protocol. And the next step we're going into now is we're going to make this stuff work with existing toolkits, which is also it's a very important step to verify that the protocol works. And then I have one more thing. So this is like something that's totally at the prototype state, but it's something that, along with client-side decorations, is the most debated topic for Wayland. Of course, we're talking about remote display here, because how can we do a new display server and not do remote display? We're crazy. But it is possible to do with Wayland, and it's very similar to how that the screen capture works. That we know exactly what we're rendering on screen, and we also know exactly what changes in every window. So we can take one window and read out the contents of that window and send off to somewhere else. When something changes in that window, we know exactly what changed in that window. We can read out only that little rectangle and send that change out over the wire. So we can forward individual windows that way. We can also, if we want to, we can just scrape the entire screen and forward the entire desktop to somewhere else. That's not something I've looked into for now, but the forwarding feature of a single window is something that I have a little prototype of here, and it gets a little confused because we need to run two Western compositors here, and this guy here has to run on a different. This is like setting a different display for X. So we set this guy runs on this socket instead, and he needs to load this module here. So here's a different compositor, and and this is where it gets confusing, because this is a Western compositor running on the Western. So this is like XNest. So think of this as XNest, right? But the idea is, of course, this guy will be running on a different system somewhere. Okay, let's try something else. We can run. We can run it as an X application too. So this is Wayland as an X compositor running under Western. So what we can do is we can grab this window and we can say forward this window to the other compositor. And now this window is out here in the main Western compositor, and it's the same window because type ls, they work the same. And I select stuff here, it happens down here. And what's interesting is that the position on the desktop is different. I move this guy around, and of course this guy stays in place here. And this is also why we can't have global coordinates, because if this guy is over here on this server, and he's over here on that server, what's the global coordinate of that window? Where do we pop up the menu? So there is no good answer to that. But as you can see, we can, and this guy could be rotated. and this guy is not rotated, we can still select here. And this is, of course, this is not remote rendering. This is sharing a window. And actually, this, if I had two laptops here, we could have one guy could be over here editing in the window, and you could have another guy over here editing. So we can use the same window. You can have each compositor have a different cursor, and they can both interact with the windows. So I don't know what two selections. Maybe you would have two selections for the terminals. So each guy can have a. But it is possible for me to type in here at the same time. Somebody could be typing over here, but it's just not easiest to demonstrate when there's only one laptop and keyboard here. And this is. In here? Well, if I close the window, the application terminates, and that means it goes away on both. So there is no way to just stop the forwarding. You can, if you stop the application, it goes away in both places. And again, it's very much a prototype, and we just scrape out the data and push it over here, and have a simple hotkey to forward the window. So there's a lot of possibilities here in how this could be done. I mean, of course, you may not want to have two windows. Maybe you just want to send it to a different server and have it disappear from this server, so you don't have the same window in two places. Or you may want to. You may want to have control over who you send it to. So if you have some kind of contact list with, you could forward it over Jabber or IRC, I don't know, some way to identify the remote server, and you can push that window to somebody you're talking to, and you can share the same window while you're chatting, and you're looking at the same window on your desktop. But I don't know, there's a lot of options here. Yeah, you can forward a root terminal over IRC. That sounds like a good idea. But yeah, so it's actually, it turns out that Wayland is optimized for no round trips, because when you're on a small device, a phone or an embedded device, you want to reduce context switches. You don't want to bounce back and forth, even though context switches round trips may be fast on a local machine, on a local connection. You don't want to, because you don't want to switch back and forth between your display server and the client several times per frame. So Wayland is actually optimized. The protocol is designed so that you ideally, if you're rendering GLX gears, or if you're doing something steady-state rendering, you schedule in the client once per frame. He processes all input events, renders, pushes the frame back to Wayland, and then eventually the compositor runs again, composites the screen, and then sends out an event to say, okay, we're ready for the next frame now. But for each frame, and when I talk about frame, we're talking about like typically 60 frames per second type of thing. So for every 16 milliseconds, you only run the client once and the compositor once. And so the whole protocol is optimized to not require round trips, that we push out state changes and so on a frame basis, and the composite and the clients will push back new frames on a per frame basis. So it turns out that this optimization, this really push to try to keep round trips down, works well for local high performance rendering, but it also works perfectly when you're trying to do low latency network rendering, because these missing round trips, or the lack of round trips, makes a big difference when you're trying to do this remotely, because you don't have to ask the server for different attributes of your rendering context or anything. You have everything local. You need to render a frame and push that across. So and I say should, because I still need to actually try this over an actual network, but it should hold up really well in face of latencies, and also in the other option, the other question, of course, what is the bandwidth of this? How many pixels do we end up? How many pixels do we end up sending per change? And again, if you're doing full screen rendering, we have to send that entire new image across every time. But we do have the previous frames, so we can do delta encoding. We can look at, even though the client told us the entire frame changed, we can go and compare that against the previous frame and just send the delta of what actually changed. And of course, we can compress that using standard techniques like either do like a full-on gzip or zlib type of compression, or what I'm doing with the WCAP format is that I'm just run length encoding it. So there are options for reducing the bandwidth uses pretty much, and more importantly, there aren't a lot of round trips to begin with. So I think it should be very efficient. It should definitely be competitive with anything X can do. And again, X is not a magic bullet either. If you're playing a full screen game over X, you're direct rendering that's not going to work remotely. If you're watching a full screen movie on X with direct rendering, that's not going to work over the network either. With X, anything you have to do network transparent has to go through shared memory or even the protocol. And that means that we just can't do that very efficiently in X either. So it's not like X can do everything with remote rendering. X, at the end of the day, it comes down to how much bandwidth are you trying to push across the network. And if you're trying to push too much, there's just no way X can do that, and there's no way Wayland really can do that. If you want to watch a movie, for example, you should probably push the media stream across and then decode it on the receiving end. Have some higher level protocol for forwarding for watching movies remotely. But I think this is a pretty good start. And for the things that people typically complain about, is that they log into a server somewhere and want to run some UI to remotely manage that server. This stuff can definitely handle that. It's like when you mouse around a button highlights, so you click a button that has to be re-rendered. There's almost no rendering traffic when doing that. So I think this should be promising. But again, this is very early state, and it's looking good, but there's a lot of work to do still. So how are we doing on time? Are we?
Well, Christian, we're really over time here.
Yeah.
But I would like to make a suggestion. So
yeah.
If we just make a brief break of 5 minutes or so that people can get coffee, or let's make it 10 minutes. People can get coffee and something to eat. And then you can continue with your second round. And then I would suggest that we have the talk that we wanted to put into the empty slot at the end of the conference today. So it would be at, let me see, it would be at 5:30 then, and then we can finish at 6 here.